All right, so today's January 24th. This is Cal 2. I want to remind everybody that a student from our class emailed me or earlier in the day today, actually talked to me online during my office hours now that I think about it, and pointed out that the page numbers on the downloaded textbook were different than the page numbers that I was supplying on homework. And what I discovered is I'm using a hard copy of the textbook, and the hard copy of the textbook and the downloaded version of the book are off by like 2 or 3 pages. The books are basically, or not basically, they're exactly the same textbook. The problems are all the same. Problem numbers are the same as far as I can tell, as far as I've been able to find, but the page numbers are off by just a couple. And so let's just make the agreement through the rest of this semester that I will just tell you what section numbers the problems are out of, and then you just need to find where they are. And on the homework sheet that I've posted for you on practice problems at the very beginning of the semester, I had both page numbers and section numbers on that. So just go by the section numbers and not the page numbers. And so I'll when the homework that's graded, I'll make sure that I identify that by section number also. And remember that the first homework assignment is due January the 28th. A single PDF file is what I'm going to be asking for. And if you go to my Google site at the very, and let me do that while we're here. Hold on real quick. That's a video we're going to look at later. So if I go to a Google site for the course, at the very bottom, you'll see links for turning in homework. The very, very bottom in the lower right-hand corner. And if you click on that, you'll get the dates that the homework is due. So January 28th, February the 4th, and everything. And all you do is click on the link, and it'll take you to my Dropbox, and you'll be able to upload your file to my Dropbox from there. And as the semester goes on, I'll just put more due dates on there so that the due date for the current homework will always be on there, and you can just go to that link. So that's the way we're going to do it during the semester. Please email me or send me a message by Remind if you have a question about that process. Okay? All right, and we'll come back to that video later in class today. Today, what we're going to do is we're going to finish up talking about volumes of solids of revolution using disks and washers. We certainly did not finish that last time. And then we will also look at volume using the shell method. And so I'm going to jump right into this and get started. And we're going to talk about some problems and work through some disk method and washer method problems, and then we'll go from there. So first of all, the disk method. And I've got some pictures already drawn on here because I wanted to kind of have some decent pictures and not have you watch me drawing the pictures and spend a lot of time doing that. First of all, remember that when you are talking about the disk method, there are two important things to deal with. You need to identify the region that you're rotating and what axis you're rotating it around. So like in this particular picture here, I'm rotating this region that I'm shading right here, and I'm rotating it around the x-axis. Right, so you can see the mirror image of that region on the other side of the x-axis. It's important that you draw in a rectangle, an appropriate approximating rectangle. And if that rectangle is perpendicular to the axis of rotation, right, if the rectangle, and I'm highlighting that, that's an important idea. If the rectangle is perpendicular to the axis of rotation, then you are using the disk method. Right, so you'll always, at the end of all this conversation that we're going to have about the shell and disk methods, one question you'll be confronted with is, well, do I use the shell or the disk method in this problem? And you look at the rectangle you're drawing and think about whether it's perpendicular to the axis of rotation or if it is parallel to the axis of rotation. If it is perpendicular to the axis of rotation, then you are using the disk method to solve the problem. And with the disk method, you are using this general form right here. And then I'm going to go ahead and put a box around right here. And this general form will work for the disk method, and it's pi r squared, which is just the area of a circle, dx. And the area of the circle is the base of that very flat cylinder that you're creating when you rotate that rectangle. So if you look at the picture that I've got on the screen, if you look at how I rotate that rectangle, and I've got what the rotation would look like off to the side there, you can see that that rectangle, and if you want to, you could actually shade in this rectangle here. This is the rectangle you're rotating right here, right? And as you rotate that rectangle around the x-axis, you're generating a very, very flat circular cylinder. And the volume for that cylinder is simply the area of the base of the cylinder times the height of the cylinder. So it'd be pi r squared times dx, or dx is actually the height of that rectangle, because the height of the cylinder. Because the cylinder, remember, is lying on its side right there. All right, and then once you've drawn in the rectangle, and appropriately, then what you need to do, right, because the form is pi r squared dx, what you need to do is identify what the radius is. And I would actually draw the radius on the picture that you're drawing. And I would label it r. Say this is the radius. And then think about whether that represents, or whether x represents the radius or y represents the radius. In the picture I've drawn right here, where I'm rotating around the x-axis, that rectangle goes all the way to the x-axis there, and so the radius is going to be a y value, right? This is a y value right here, and it's the y value on that curve right there, so it's the function value. And so you see that the volume is going to be given by the integral from a to b of just pi r squared dx, but r is y, or r is f of x, and so it'd be pi times f of x squared dx. All right, so that's the general form for a problem where you're generating a solid disk, okay? So I wanted to kind of draw that picture out, kind of walk through the process again. And we actually kind of worked on a problem like that last time in class. All right, now so I'm going to flip the screen here. If the region that you're talking about does not go all the way to the axis of rotation. Okay, so in this problem, the axis, or this picture rather, the axis of rotation is the x-axis. But I want you to look at the region that you're rotating. That region, and I've got it shaded there on this picture, does not go all the way to the x-axis. So notice that this representative rectangle I've got drawn right here does not go all the way to the axis of rotation. And you can see the mirror image of that rectangle on the other side of the x-axis. Here's the mirror image down below the x-axis. So what have you got here? That this rectangle, actually, as you rotate it around the x-axis, generates a disk with a hole in it. Here's our rectangle right there. Make it a little bit skinnier probably. And that rectangle, right, I'll shade it, is the same rectangle I have drawn in the picture over there. And as you rotate it around the x-axis, notice you're actually generating a disk that has a hole in it, right? So this happens when the rectangle does not go all the way to the axis of rotation. And notice I've got that already written on here. So I'm going to highlight that because it's important that the washer method is really the same as the disk method, except that the rectangle that you've got does not go all the way to the axis of rotation. Notice that the rectangle is perpendicular to the axis of rotation, which is the x-axis, but it doesn't go all the way to the x-axis like this previous picture did right here, where if you look at it, this rectangle went all the way to the x-axis right there. All right, so that's the difference between the disk method and the washer method as far as the picture, right? Now, what happens here, that the volume of the washer, right, if you're talking about a volume of a washer, that's going to be in this box here at the top right here, is going to be a subtraction problem. And it's going to be the volume of the solid disk. If you had a disk with no hole in it, it'd be the volume of that disk minus the volume of the hole, because it's like you're pulling that hole out from the from the middle of that disk. And so notice I've got the little subtraction problem there. It's the volume of the solid disk minus the volume of the hole. So if you look down below the picture, here is the volume of the solid disk. Whoa. Here's the volume of the solid disk right here. Pi times big R squared dx, where big R, if you look at the picture, is the radius of the solid disk right there. So there's big R. And then little r is the radius of the hole. And so you have to use, and it's a subtraction problem here, and you're taking the volume of that solid disk and subtracting away the volume of the hole. And so this is, notice very similar integrals. It's pi times big R squared dx for the first integral. The second integral is pi times little r squared dx. And notice since the limits of integration are the same, you could really combine that as one integral. And so this is the form for the washer method that we are typically going to write down, is that when you do generate a washer, a disk with a hole in it, that the integral is simply going to be, the integral for the volume is going to be pi times the integral of big R squared minus little r squared, where big R is the radius of the solid disk, the big disk, and little r is the radius of the small disk or the hole, right? And then if those are function values, then you just substitute in the function values there, like I did at the very end. And again, I would, on the picture, I would draw a rough sketch of the picture and of the region that you're talking about. Now, you don't need the disk drawn off to the side like I'm doing there. That's okay. You don't need to do that. But I do want you, to get in the habit of labeling big R and little r so that you can see them on the picture. All right, so that walks through the washer method, and now we're ready, hopefully, to you kind of have a setup on how this is going to work. And so now we're going to actually look at some problems, some actual problems, and work through several examples, and hopefully answer some questions as we're going through this also. All right, here's our first problem, and I've got the picture drawn already, but none of the work here. We want to look at the region bounded by the curve y equals 4 minus x squared over 4. So here's one curve right here. Here's one function. And y equals 2. So we want to look at that region that's bounded by those two curves, and we're going to rotate that around the x-axis. And when we do that, we want to find the volume of that solid. And if you think about the way that solid's going to look, right, it's kind of like, what I would say is it's kind of sort of like a donut, except the donut, if you cut through a donut has rounded edges on both the outside and the inside. This donut has rounded edges on the outside, but has a vertical edge on the inside. But it's sort of like a donut anyway. So what I did is I took the liberty of actually finding the points of intersection for this curve, and I already did that arithmetic right here. Put a box around that. Right, these are the points of intersection. And so I set the two functions equal to each other. 4 minus x squared over 4 equals 2. I solved for x, and I got plus or minus the square root of 8. So the 2 points of intersection of those two graphs I've got right here are negative 8 square root of 2 and positive 8 square root of 2. And I drew in the representative rectangle in there. And so now what we're going to do, and I actually draw a cross-section of that rectangle also. And so now what we want to do is we want to look at little r and big R and label those on this picture. So over here on the, I'm going to go ahead and draw in the axis there. On the little disk I've got drawn off to the side, little r would be this distance, and big R would be that distance. Little r, remember, is the radius of the hole. Big R is the radius of the big disk, of the solid disk. So on my picture, if you look at the picture, little r is represented by that distance right there. So let's think about, before we draw big R on the picture, let's look at little r. Now notice, no matter where you put little r is always the same. It's always that inside curve, and that inside curve is just the function y equals 2. And so from the picture, in this problem, little r is equal to a constant. It's equal to 2. It's that inside curve. It's always equal to 2 no matter where you drew little r. Big R is this distance right here. And big R is the radius of the outside of this disk. And that's governed by that green curve I've got there. That's our function 4 minus x squared over 4. And so big R is the function 4 minus x squared over 4. On the previous picture, I labeled one of them f of x and g of x, and that's what these functions are. You've got little r is g of x, let's say, and big R is f of x, right? It's just the function values. They're both y values because notice big R and little r are both drawn from the x-axis. And since they're both drawn from the x-axis, they're just y values is all we're talking about. And I'm going to kind of make these x and y-axis maybe a little bit more solid so that they kind of stand out. So that sometimes it's easy to kind of lose sight of where the axes are when you're drawing pictures like this because you've got so much going on there. So there's my x and y axis right there. So big R and little r are both drawn from that x-axis, and so those would be y values. All right, see, so we are ready to write down the integral for the volume here because remember from the previous page we've got that the volume would be the integral from a to b, pi times the integral from a to b of big R squared minus little r squared dx. Because we're integrating, this is a vertical rectangle, so we're integrating with respect to x. So all you're doing is substituting the values in here. You've got, this is going to be pi times, and by the way, notice that this solid, because it's symmetric around the y-axis, because the region is symmetric around the y-axis, I could really just integrate this problem from, not from negative square root of 8 to positive square root of 8, but from 0 to positive square root of 8. And let me show you. So this is what you might start off with, is negative square root of 8 to positive square root of 8. And it'd be pi times big R squared, which would be 4 minus x squared over 4, quantity squared, minus little r squared, which would just be 2 squared, like this. And this would be dx right here. But what I want you to see is that when you have a symmetric solid like this, in other words, when the region is symmetric around the y-axis, it is okay to integrate not across the entire region, but just to integrate across half the region and go from 0 to the square root of 8, square root of 8, and then just multiply that integral by 2. So notice I've got a 2 sitting out in front, and it's got a 2 pi there. And then this is times 4 minus x squared over 4 squared minus 2 squared, like this. I would take advantage of that because when you have 0 as a limit of integration, it just makes the arithmetic much easier at the end of the problem. So I would definitely take advantage of that. All right, so we've got the integral set up from the picture, right? And so now we're ready to tackle the actually evaluating this integral. So we go 2 pi times the integral from 0 to the square root of 8, and we square out that 4 minus x squared over 4. I would just go ahead and square it out. That's not too bad. It's technically, you know, the FOIL method because it's 4 minus x squared over 4 times 4 minus x squared over 4. And if you feel like you need to write that out off to the side, then that's okay. You could do that, right? If that's going to help you keep it straight, I don't have a problem with that at all, right? Take 4 minus x squared over 4 times 4 minus x squared over 4, like that. All right, so our volume integral is going to be, let's see, we're going to get 16. And then if you think about it, the cross products there on the FOIL method, in both cases you get 4 times x squared over 4. The 4's cancel, so notice in both cases you get an x squared. And so this is just going to be minus 2x squared, and then plus x to the 4th over 16, like that. And then this would be minus 4, and then dx, like that. And then collect like terms. So you're going from 0 to square root of 8. And let's see, 16 minus 4 is 12. So you have 12 minus 2x squared plus x to the 4th over 16 dx, like that. And now we're ready to write down the antiderivative using the fundamental theorem. So you keep this 2 pi out in front like that. And then find the antiderivative. You get 12x minus 2/3 x cubed plus, okay, so let's see, so that's going to be x to the 4th, it's going to be an x to the 5th, and then you're going to have a 1/5 in front. So this is going to be x to the 5th over 80. And then this is going to be from 0 to the square root of 8. Like that. All right, and you can do some simplifying here if you want. You remember that anytime you've got a square root of 8 squared, don't forget that anytime you have a square root of 8 squared, that's just an 8. So you might look at how many square root of 8 squares you've got in there as you evaluate this thing. So you have 2 pi times 12 times the square root of 8 minus 2/3 times the square root of 8 cubed, and then plus the square root of 8 to the 5th power over 80, like that. And simplify this so that it's reasonable. If you wanted to find a decimal value using your calculator at this point, you could do that. If you want the exact value and leave it as in radical form, you could do that also. And also remember, don't forget also that the square root of 8 is really 2 times the square root of 2, because it's the square root of 4 times the square root of 2. So, you could think of that as well as far as how you write it out. So, let's see, you've got 2 pi, and then 12 times the square root of 8. Square root of 8 is 2 times the square root of 2, like I said, so that's really 24 times the square root of 2. I'm just going to write everything in terms of the square root of 2. Minus 2/3. And then the square root of 8 squared is 8, so you have 1 8 in there, and then you still have another square root of 8, which is a 2 square root of 2. It's kind of yucky arithmetic here. And then finally the square root of 8 to the 5th power, well, there's 2 square roots of 8 squared in there. So that's an 8 times an 8, and then you have 1 square root of 8 left, and that's a 2 times the square root of 2. And that's all over 80. So this can be done. You just have to be patient. It's going through the arithmetic here. So you have 2 pi times 24 square root of 2 minus 16/3. Right, you got that 16/3. I'm sorry, it's not 16/3. It's 32/3. Sorry about that. Because you have a 2 times an 8 times another 2. So that'd be 32. I get it. So to be 32/3 times the square root of 2. And then the last one, let's see, I've got a bunch of stuff cancels here. Right, the 8 and the 80 cancel and leave me the 10. And then the 2 and the 10 cancel and leave me the 5. And so that last term is going to be 8 times the square root of 2 over 5. Eight times the square root of 2 over 5, like that. All right, and then at that point, you could, so at that point, you could go through and simplify this. And if notice that they're all square roots of 2 in there. And so what you're going to end up with here, I'm going to put dot, dot, dot. But you're going to end up with a 2 pi times some coefficient times the square root of 2, like this. And that's going to all be divided by 15, because that's going to be the least common denominator. And that's certainly something I would want you just to finish up the arithmetic there. I don't really see a lot to be gained from trying to go through that kind of messy arithmetic on the video here. All right, so we've got a good problem worked out with the washer method, right, where we generated a disk with a hole in it. So we are going to move on and look at another problem, a different situation. All right, so in this case, we are we've got a region bounded by the curve y equals the square root of x, and y equals 0, which is just the x-axis, and then x equals 3. So I've got the region that we're rotating shaded, and it's rotated in this case around the y-axis. So notice because I'm integrating or rotating around the y-axis, I use a horizontal rectangle in this case, right? If I'm using the disk method, remember I want my rectangle to be perpendicular to the axis of rotation, but the axis of rotation is this y-axis. That's an arrow showing the rotation there. And so I am going to use a horizontal rectangle, since that's perpendicular to that axis of rotation. And notice if I use a horizontal rectangle, this problem is going to generate, again, a disk with a hole in it. Now here would be the rectangle up here on in the coordinate system in our picture. And then down here, this is the rectangle right, that's rotating, right? It's that same rectangle, just I'm just kind of projecting it down below so we can actually see that rotation. And so we're rotating it around, and we're definitely generating a disk with a hole in it in this picture. All right, so we do know that the volume in this problem, because it's a disk with a hole in it, we know that the volume is going to be the integral from a to b of, and pi times the integral from a to b of capital R squared minus little r squared. In this case, it's going to be dy, because dy is the width of that rectangle right there, right? When you use a horizontal rectangle, remember you integrate with respect to y. All right, so now the next thing we need to do is draw the pictures so that I can see where the radii are going to be in this problem. So here, down below is our little disc with a hole in it, our washer down there. And the inside radius is this distance right here. That's little r. And big R would be this distance right here, all the way out to the edge of that rectangle. That would be big R. So in my picture up here, I'm going to put these maybe in a different color so they stand out. This is little r right here. And this is big R. All right? And so in our problem, big R is going to be a constant, right? Big R is going to be 3, right? So big R is equal to 3. It's always, that rectangle on the outside is always bounded by 3. It never changes. And on the inside, little r is equal to x, right? Because it's measured from the y-axis. It's an x value. And what is x going to be equal to? That's why I took my curve, y equals the square root of x. And notice what I did is I solved it for x because I needed an expression in terms of y for x here. And so that would be y squared, right? So x is equal to y squared, and that would be little r. So in my problem here, the volume, and this is not a symmetric region of any type whatsoever, so I'm just going to deal with the integral like it is. I'm going to have the volume to be pi times the integral from, and I do need the limits of integration, so I want you to look at the curve that I've got there, and look at that rectangle and how the rectangle varies from bottom to top. Right, and the rectangle varies at the y value 0 on the bottom of that region, and then this point of intersection right here on the curve, remember that point right there has got an x value of 3 and a y value of the square root of 3. Right, and so that would be my upper limit of integration would be the y value of that point, would be the square root of 3. And then big R squared would be 3 squared, and then little r squared would be y squared squared. This is a much simpler integral than the last problem. dy like that. Right, and so we've got the integral set up. We are ready to go on the problem. So this would be pi times the integral from 0 to the square root of 3 of 9 minus y to the fourth. A pretty simple integral. Like that. So don't think that they're always going to be really horrible. Now, sometimes they are going to be horrible, but that doesn't necessarily mean they're always going to be like that. So the volume would be pi times, we write down the antiderivative, would be 9y minus 1/5 y to the fifth, and the limits of integration would be from 0 to the square root of 3. And so continuing over here on the right, the volume would be pi times 9 times the square root of 3 minus 1/5 times the square root of 3 to the fifth. Like that. And the lower limit's going to be 0. So I don't even have to worry about the lower limit here because that's 0. All right, don't forget that the square root of 3 squared is 3. So in this case, you got pi times 9 times the square root of 3, and then you have minus 1/5, and then you have 2 square roots of 3 squared in there. That would give you square root of 3 to the fourth. So there's 2 3's in there. And then you still have a square root of 3 left. And if you have problems with that, this is what I'm doing. Let me put that in a different color. Make sure everybody understands the arithmetic there. Square root of 3 to the fifth power, I'm really saying, is the square root of 3 squared times the square root of 3 squared times the square root of 3. Right? And that's where I get 3 times the square root of 3. And that's what I've got right here. Right? So that's how that arithmetic is working out. All right, so our volume would be pi times 9 square root of 3 minus 9/5 times the square root of 3, like that. And then I'd get a common denominator, which would be 5. So you have 45/5 square root of 3 minus 9/5 square root of 3. And so that would give you volume to be, let's see, 45/5 minus 9/5 would be 36/5. And then you'd have a pi in there, and then times the square root of 3. And that would be cubic units there, you know, and because we're finding a volume, technically I should take off or penalize you if you don't write cubic units down at the end. But I'm probably not going to make a big deal about that, just so you know. All right, so there's a good problem right there with the disk method. So hopefully, and I say disk method, but technically the washer method on that problem. So hopefully everybody's okay with that, and there's no questions there. All right, and Jaime, do you have a question by any chance while we're talking about that problem? No. Okay. So hopefully this is kind of clearing things up for Jaime, for you who are watching live, and for anybody out there who's watching the recorded version of this. Hopefully that's straightening some things out. All right, now this problem is a little bit different. Notice we're taking the same region we just had in the last problem, but instead of rotating around the x-axis or the y-axis, we are now rotating around the line x equals 3. So this is our axis of rotation. Is not one of the axes, right? Here's the x-axis right here. Here's the y-axis right here. We're taking the same region we had in the last problem. So this is y equals the square root of 3 here, or not y equals the square root of 3, sorry, y equals the square root of x. Or y squared is equal to x. But we're rotating it around the vertical line x equals 3. So that's my axis of rotation. Okay, so that's different. So notice I have a cross-section drawn out. And notice that the rectangle that we've got drawn in that region does go all the way to the axis of rotation. So this is not a washer. This is just a solid disk. Oh, and I've already got the word solid disk written there. So this is just a solid disk in our problem, right? And so our integral in this case is just going to be the integral from a to b of pi r squared dy, right? Where r is just the radius of the disk that you're talking about. So in my problem, r, and remember we always draw r from the axis of rotation, since everything's rotating around that axis. So little r, or it doesn't have to be little r in this case, it's just r, is that distance right there. That's our radius. Notice it is not drawn from the y-axis. And what we need to do is come up with an expression that involves, that is in terms of y, that will represent r in that picture right there. All right, so now what I want you to do is look carefully at the picture. So I've got r as that green arrow, and then the pink arrow right here out to the rectangle. Well, that's from the y-axis, and so that would be x right there, that distance. So I have r and I have x right there. All right, and then finally, the total distance right here. Now let me put that in still a different color. The total distance right here is a constant because it's out to that vertical line. That's 3. And notice from the picture then what you have is that x plus r is got to be equal to 3. And so in our problem, r would be 3 minus x. And x is equal to y squared, so r would be 3 minus y squared. That's our expression for r. So that's a little bit different. You had to try to piece things together there to try to write down an expression for r. And the reason why you had to do a little bit differently on this problem is that r was not drawn from the x-axis or the y-axis. It's always drawn from the axis of rotation. And the axis of rotation happens to be another line, if not one of the axes. So you had to be kind of careful there. All right, so now let's write out the volume integral here. So the volume integral in this problem would be the integral from, just like the last problem, it'd be 0 to the square root of 3. And this would be pi times the square of the radius, but the radius is 3 minus y squared. So this would be 3 minus y squared squared dy. Okay, and so there's our volume integral in this problem. Not too bad of an integral here at all. The volume would be the integral from 0 to the square root of 3 of pi, and let me go ahead and take that pi outside the integral there. Put the pi out here. Square out the 3 minus y squared, which would be 9 minus 6y squared plus y to the 4th dy. So not too bad of an integral. It's just a polynomial. So you'd have 9y minus 2y cubed plus 1/5 y to the 5th. And that would go from 0 to the square root of 3. The lower limit would be 0, so you don't have to worry about that. Upper limit, you get 9 square root of 3 minus 2 times the square root of 3 cubed plus 1/5 times the square root of 3 to the 5th power, like that. All right, and remember we've talked about this on the last screen. Square root of 3 cubed is really the square root of 3 squared times the square root of 3. And so that's 3 times the square root of 3. And the square root of 3 to the 5th is really square root of 3 squared times the square root of 3 squared times the square root of 3. So that'd be 3 times 3, or 9 times the square root of 3. So in our problem, this would be pi times 9 square root of 3 minus, and then the square root of 3 cubed, we've already said, is 3 square root of 3 times the 2, so that'd be 6 square root of 3. And then plus, the last one would be 9 square root of 3 over 5. Like that. Right, and you would, let's see, you could take the first two terms and combine them. Probably that would be what I would do first. So you get 3 square root of 3 plus 9 square root of 3 over 5. And then go ahead and get a common denominator, which is 15. I'm sorry, which is 5. And so you have 15 square root of 3 plus 9 square root of 3 over 5. And so finally the volume is going to be 24 square root of 3 over 5 times pi. And again, cubic units. And that would be our volume for that solid we are generating right there. All right, so let's see how we're doing on time here. I wanted to make sure that we left plenty of time to talk about the shell method. And so I think that's what I want to do next, is look at the shell method. And because we've gotten through quite a few disk method problems now. Hopefully this is all maybe starting to make more and more sense every time we go through an example. All right, so I've got the pictures here. Let's talk about the shell method. And I've got the picture drawn out already. So let's say we're taking this region that I've got shaded right there, and I'm rotating it around the y-axis. Now look at the rectangle I have drawn. Notice that the rectangle is parallel to the axis of rotation and is not perpendicular to the axis. Remember, the axis of rotation here is the y-axis. The rectangle I drew in the region was parallel to the y-axis. So it would not be a disk method problem, because when you do disk method, the rectangle, remember, has to be perpendicular to the axis of rotation. All right, so I draw this representative rectangle in the region right in here, and this would be the rectangle down below in the picture. And as we rotate that around the y-axis, notice that I'm not generating a disk. What I'm generating is what we call a shell. And the shell has got a wall, right? And the wall has got the thickness that is represented by that rectangle that we were rotating around. Now the rectangle itself, if you look at the picture, its area would be the height of the rectangle dx. And so I get this expression h dx for the area of the rectangle right there, right? And all right, and then if you think about the fact that that rectangle is actually rotating around the y-axis, the distance that that rectangle is rotating around the y-axis is the circumference of that circle. And so that'd be 2 pi times the radius. And so the volume of that shell is simply the area of the rectangle multiplied by the distance the rectangle moves around. And so it's 2 pi r times h. And so we use that expression there, and we end up getting the volume as a shell method problem, where this is the distance it's traveled. This is the circumference right here, is 2 pi r. And h dx represents the area of the rectangle. All right, and let's see. All right, so we've got our formula here for the shell method, right? So shell method, a couple things to think about with the shell method. First of all, shell method you use when the rectangle you're drawing is parallel to the axis of rotation. So that's how you tell the difference between a shell method problem and a disk method problem. Is the shell method, the rectangle is parallel to the axis of rotation. The disk method, the axis is, or the rectangle is perpendicular to the axis of rotation. Probably not a bad idea to write those two statements down right next to each other, right? So shell method, you've got this integral, the integral from a to b of 2 pi r h dx. and the rectangle is parallel to the axis of rotation. The disk method, the general form would be the integral from a to b of pi r squared dx. And in this case, the rectangle is perpendicular to the axis of rotation. Now, there are many problems, by the way, where you could work the problem either as a disk method problem or a shell method problem. And sometimes, sometimes it doesn't matter which way you do it. Sometimes one of them is definitely easier than the other. So as you're going through these problems, if you set up a problem and it looks like it's really going to be a difficult integral, then try the other method and see if you get an easier integral. All right, once more I need to just send a text here because somebody's trying to set up their audio. All right, and so let's go ahead, excuse me, and let's go ahead and look at some problems with the shell method, and let's see how this works out. All right. DeMarco, can you hear me?
Yes, sir. I sure can.
Okay, there you go. We're pleased to have you. It looks like you called in with your phone.
I did. Yes, sir.
Okay.
I sure did.
Next time when you log in, you should be given the option. I don't know if you have a computer that has an internal speaker and microphone and all that stuff, but if you do, when you log in, you will be given the choice of calling in with the computer, and most students find that to be...
Yeah, I had the kids in the background making a lot of noise. I did want to disrupt you guys, so I just wanted to just go ahead and call in.
Hey, you do whatever you think is the most convenient for your personal circumstance. That's definitely okay. Well, we're glad you joined us. We're kind of in the middle of lecture right now. We're talking about, we just finished the disk method, and we're going into the shell method for finding volume. So, and I've kind of got some pictures drawn out here for the shell method, and now we're going to work through some problems that involve the shell method, and then we'll actually look at a problem somewhere along the line too where we compare shell and disk and see which one might work better. So
okay, awesome. I'll just catch up and watch the recorded video as far as what I've missed thus far.
Okay, great, DeMarco, and please, and Jaime is the other person who's on with me right now. Just like I've told him many times, but if you see something and you're not sure what I'm doing, or if you have a question, just like a face-to-face class, you stop me and say, hey, I don't understand what you're doing, and that would be fine. So, okay?
Okay, awesome. All right. Thank you.
Okay, yeah, you're welcome. I'm glad you're here. All right, so this is our problem. We're going to take this region. Let's say we've got the equation y equals negative x plus 1. All right, so negative x plus 1 is just a line, right? And let's look at the region that's bounded by y equals negative x plus 1 and x equals 0 and y equals 0. In other words, the two axes. All right, so as we go into this problem, we'll talk about how this works. We want to specifically practice shell method on this problem for sure. All right, so this is just a line that has an intercept at 1 and another intercept, that's the y-intercept, and then the x-intercept is also at 1. So 1 and 1 right there, and here's our line. So we're talking about the region that's bounded by that line and the two coordinate axes. So this is the region we're talking about. It's just this triangle. Okay, and so what we're going to do is we're going to rotate that triangle around the y-axis. And so we want to find the volume. And we want to find the volume using the shell method. All right, so we know that the volume using the shell method generally is given by this integral, the integral from a to b of 2 pi r, right, the circumference, remember that's what that represents, times height, dx or dy, depending on the problem. So if we're going to use the shell method, and we're talking about the axis of rotation being, around the y-axis, remember what we were talking about in the last screen, that would mean that our rectangle has to be parallel to the axis of rotation, and so that's our rectangle right there. Right, that's the rectangle that we're rotating. And we're rotating around the y-axis, so we need to label r and h on my picture here. So the r, remember, radius is always drawn from the axis of rotation. So r would be this distance right here, little r. And in this case, it's not a distinction between little r and big R. So if you wanted to use a big R, you could. And then the height of the rectangle is simply that distance right here, h. So what does r represent here? If you think about it, little r is just the distance from the y-axis, and so little r would have to be x. And h is simply the distance from the x-axis, and so h would have to be y. And so our volume in this case, we can be a little bit more specific now, is going to be the integral from, and think about that rectangle and how it varies across that region. As it shifts across the region from left to right, it's going to go from 0 to 1. And this is going to be 2 pi times r, but r is x, and times h, but h is y, and then this would be dx. So there's our integral. Now, obviously, the issue there with the integral is that it's got an x and a y in it. But what do we know about y? Well, remember, y is just represented by that line. And so y is equal to negative x plus 1. And so our volume is going to be the integral from 0 to 1 of 2 pi times x. And then in place of y, we write negative x plus 1. And then that'd be dx. And there's our volume using the shell method, right? So again, remember that the shell method has two pieces to it. When you write out the integral, you've got the circumference of the circle. In other words, the circumference of the total distance that rectangle has traveled, and then that's times the area of the rectangle itself, which is just the height of it times the width of it, which would be h dx. So it always comes in those two pieces right there. All right, so the volume, let's go ahead and kind of continue this over here. The volume is going to be, multiply this out, you get 2 pi times negative x squared plus x dx. And we can take out the 2 pi. And then the antiderivative is easy to do in this problem, no question about that. So this would be 2 pi times negative 1/3 x cubed plus 1/2 x squared. And that's from 0 to 1. This one's really easy compared to some of the ones we've done where the arithmetic was horrible. Put the 1 in there and you just get negative 1/3 plus 1/2. Put 0 in there and you get 0. And then finally you get a common denominator to add those together there, and you get, what's that? That's going to be negative 2/6 plus 3/6. So you get 2 pi times 1/6, or pi over 3. That'd be pi over 3 cubic units. Now, I do want you to think about whether that makes sense. Pi over 3 cubic units is just simply a a little bit more than 1 cubic unit, because pi is just a little bit bigger than 1. So the solid that we're generating better not be very big, because its volume is only 1 cubic unit. But if you look at the picture, remember that the intercepts just go out to 1 and 1 on the x and y axis. So this is a pretty small solid that we're rotating around the y-axis when we generate it around the y-axis, right? Because we're getting a cross-section over here like this, and all we're getting here is a right circular cone, right? And by the way, you know, if you wanted to check this using geometry, you could, because the solid that you're generating ends up being a cone that looks like this. Right, and the volume of a cone, I don't know if you remember this or not, but the volume of a cone is 1/3 times pi r squared times h. R is the radius of the circle on the bottom, which in this case, the radius would be 1 if you look at the picture up there. And the height is just the height of the cone, which is 1. And so notice you get 1/3 times pi times 1 times 1, and sure enough, you get 1/3 pi. So this is a problem where we could actually check the volume of that thing, because it ended up being a regular geometric figure, which doesn't happen very often, but in this case it did. So we might as well take advantage of that a little bit. All right, so we want to look at another problem. We think, yeah, we definitely have enough time to do at least 1 or 2 more things here as far as. So I'm hoping to get through 2 situations here before we finish up. The next problem I want to look at, we're going to actually compare the shell and the disk method. So in this next example, we're going to look at a comparison of shell and disk. All right, so let's say we have the function y equals 1/2 x squared plus 1. And we're talking about the region that's inside that curve, and the y-axis, and y equals 3, and x equals 2. So clearly one thing you want to do here is you want to draw a picture out. So, and probably don't need to draw it over there, draw it over here. You definitely want to draw a picture of this thing, see what it looks like. All right, so you have y equals 3, right, is this horizontal line. There's y equals 3 right there. All right, and by the way, well, let's look at the region, and then I'll tell you the axis of rotation here. And then 1/2 x squared plus 1, right, if you think about this for a second, if you go out to 2 right here, 1/2 x squared plus 1 is this parabola. And the parabola, remember, it's 1/2 x squared plus 1. When x is 2, you just get 3, and you get this point right here. So you have this parabola that looks like this. And this parabola just kind of continues on like that. But we're talking about this region right in here. I'm shading it in blue. All right, so I'm talking about that region, and what we're going to do is we're going to rotate that region around the y-axis. So we're going to rotate around the y-axis. And let's look at shell and disk on this problem. So what I'm going to do before I do anything else, I'm going to copy this picture. Since I've already drawn it, I don't want to have to draw it again. Copy that, paste it. We're going to paste it kind of down below here. All right, and so we're going to use the shell method first of all on this problem and see how the shell method will work. Remember, the axis of rotation is the y-axis that we're rotating around. All right, so in the shell method, what kind of a rectangle do we want? Remember, in the shell method, the rectangle has to be parallel to the axis of rotation. So there's my rectangle in there. And you're rotating that around the y-axis. And so the radius, you have to label or find r and h here to set up the shell method. Remember the general form for the shell method is volume equals the integral from a to b of 2 pi r h dx in this case, because we're integrating with respect to x. It's a vertical rectangle. Remember, vertical rectangles, you're integrating with respect to x. Okay, so on my picture, r is this distance right here, because it's the distance the rectangle is from the axis of rotation. So that's little r, and so little r in this problem would be equal to x. Easy enough. And then height, well, height is this distance right in here. It's the height of that rectangle. So that's the height right there. That's h. And so this is one we're going to have to piece together a little bit. This total distance here, since that is a horizontal line, that total distance is always 3. And this distance right here, since it's from the x-axis, remember the distance from the x-axis is always a y value. And so what we have here is that h plus y is equal to 3. Right? When you take h and y and add them together, you always get 3 because it's always going to be a constant. And so now you need an expression for h, and so you got that h is 3 minus y. All right, so we can use that now. So what do we get here? The volume is the integral from, and we're integrating with respect to x, so we sweep across from left to right. This point right here is at the point 2, 3. So the integral is going to go from 0 to 2. And it's going to be 2 pi times r. R, remember, is always the distance that rectangle is from the y-axis. And so r would be equal to x. And then we had to go through that little bit of a calculation to figure out h. And h was 3 minus y. And once again, what's the issue there? It got a y in the integral, and so we replace y, right, with 1/2 x squared plus 1. So volume is going to be the integral from 0 to 2 pi x times 3 minus, and then this would be 1/2 x squared plus 1. Close off the parentheses there, dx. So a little bit of work to do there. It's not the worst thing in the world, but let me go ahead and take the 2 pi out in front of the integral. And then this is 2 pi x times, in parentheses, let's say you're going to have 3 minus 1 in there because you distribute that minus sign through, right? The minus sign gets distributed through. So you get 2 minus 1/2 x squared dx. And for some reason I wrote down, I just noticed the 2 pi twice in there. I can erase that. There's just an x right there. Right? And so finally the volume is going to be 2 pi times the integral from 0 to 2 of 2x minus 1/2 x cubed. Not bad. And so that would be 2 pi times x squared minus 1/8 x to the 4th. That is from 0 to 2. And that arithmetic is not bad right there, because that's 2 pi times 2 squared is 4. And 2 to the 4th is 16 times 1/8 would be 2. And so you end up with 4 pi as the answer. 4 pi is our answer. So that's the volume of that solid there. And that was using the shell method to do that problem. Now, let's see. Let me...
Dr. Polito?
Yes, please. Mr. Polito, but
Hey, really?
thanks for the promotion. But yeah, just Mr. Polito. What's up?
Oh, quick question. How do you make a determination whether or not to use the shell or the disc?
That is the $64 question right there, DeMarco. and there is no real there's no real solid answer to that question, to be honest with you. All you can say is that in some, look at the rectangle you're drawing and see if the because the rectangle is going to be determined in the problem, because you know that if the rectangle is parallel to the axis of rotation, it has to be shell method, and if the rectangle is perpendicular to the axis of rotation, it has to be the disk method. So sometimes when you draw the rectangle, right away, this isn't going to work very well because I don't have nice expressions at all for the bounds on the rectangle. So sometimes the answer is really obvious that there's no way it's going to work. And then sometimes you really don't know until you get into the problem. You start writing it out using the shell or the disk method, and then as you go through the problem, somewhere along the line you hit a bump and you go, gee, I don't even know what to do with the integral anymore. And so then you bail out and try the other method. And then sometimes it doesn't matter. Sometimes in both cases, it's a reasonably easy integral to deal with, and it's really reasonably easy to set up. So that's actually a good question and not an easy answer at all. And I know I kind of danced around it, and the reason is because there's not really a good solid answer to the question. What I'm going to do here over these last two problems is I'm going to show you a problem, two pictures. So this is one of them, and then we'll have time for another one in a second. And I'm going to work at both shell and disk so you can kind of see the difference. And in some cases, let's say you and Jaime are the two that are watching me live right now. You both work the same problem, and one of you sees it as a disk method problem, and one of you sees it as a shell method problem. Sometimes it's the easiest method is just the method that you see, and everybody sees it differently sometimes, and so it just depends on how that works out, So let's work through the disk method here, and let's see if you see a difference between the two, and you think that one is easier than the other one. Unfortunately, going into the problem, a lot of times there's not really an easy way to know whether that's true or not. All right, so here is disk method. So notice in the disk method, I'm drawing a horizontal rectangle because the rectangle has to be perpendicular to the axis of rotation. Okay, so let's label the picture. In this case, we know that the volume using the disk method has got to be the integral from a to b of pi r squared dx. This is definitely not a disk with a hole in it. It's definitely not a washer, so we don't have to worry about that at least. And on my picture, all I've got to do is label r, and here's r. Right, that's the radius of rotation right there. And since r is a distance from the y-axis, r is automatically equal to x. Now, you have to do a little bit of work there, don't you? Because I don't have x as a nice value here, right? If you think about this for a second, when you write out the volume integral, this is going to be the integral from, look at that red rectangle in that picture. It's going to go from y equals 1 to y equals 3. So this is going to go from 1 to 3. And then it's going to be pi times the square of the radius, but the radius is x. Unfortunately, this is dy. Oh, wait a minute. I just noticed in the general form for the disk method, I wrote dx there, but this should be dy because the picture, it was a horizontal rectangle. So that's definitely the width of that rectangle is dy right there. I'm integrating with respect to y. So what's the problem here? The problem is I'm integrating with respect to y, but the expression involves x. And so I've got to solve for x here. I've got y equals 1/2 x squared plus 1, and so I've actually got to solve that thing for x. So I subtract 1. I multiply both sides by 2, and I get 2y minus 2 equals x squared. And then I got to take the square root, and I get 2y minus 2 is equal to x. Technically, it's plus or minus, but x is positive on my picture, so all I need is the positive square root there. So x is the square root of 2y minus 2, and sometimes like DeMarco, you were asking me about this a second ago. Sometimes that's a killer right there. As soon as you see a radical in there, you know that the integral you're going to come up with is going to be kind of gross. But notice in this problem that doesn't happen, because look what happens. You have pi times x squared, but x is the square root of 2y minus 2. And so notice the radical just drops out. And you have the pi times the integral from 1 to 3 of just 2y minus 2. So you end up with a super easy integral, as it turns out. So the volume is pi times y squared minus 2y from 1 to 3. There's another difference between the disk and the shell, is the shell had limits of integration from 0 to 2. Disk had limits of integration from 1 to 3. So I don't get a 0, you know. Doesn't matter too much, but so volume is pi times upper limit would be 9 minus 6. And then lower limit would be 1 minus 2. So that wasn't too bad. And I better, by the way, before I finish this, I better end up with 4 pi as the answer. If I don't end up with 4 pi, I know I've done something wrong on one of them, because they better agree. So this is pi times 3 minus negative 1, so it's 3 plus 1. And sure enough, I end up with 4 pi. So notice, DeMarco, in this case, it worked both as shell and disk. Each one had some issues with it. You know, on shell method, I had to worry about piecing together how to find h. So I had to do some work to find the height. On the disk method, I had to do a little bit of work to solve for x and got a radical, you know. But neither one of them was real difficult, but, you know, there wasn't an obvious winner in this case. As far, if this was a competition, I would look at this and I'd say, you know, it's 6 1/2 dozen of the other, pretty much. All right, let's finish this with one more picture here, and this is just going to take us a few minutes to go through. Let's say I have y equals x squared and y equals x cubed. And I'm looking at the region that's bounded between those two curves. And I'm just going to go ahead and draw out a rough sketch here, and we're just going to use one sketch for this problem. 1, 2, 3, 4, 5, 6. So let's say that that's 1. That's 1 right there. So y equals x squared, we know, is this parabola. So there's x squared. X cubed is a cube graph. And so it goes through 1, 1 also. It's just, and I'm going to exaggerate this, by the way, to make it more obvious. But x cubed kind of looks like that. And they both go through the point 1, 1. And so what I want to do is I want to take this region right in here, and I'm going to rotate this around the y-axis. So we're going to rotate around the y-axis. And I'll just use shell and disk with the same picture there. So with the shell, I know that the volume is going to be the integral from a to b of 2 pi r h. And let me not write down dx or dy just yet. We're rotating around the y-axis. That's our rotation. So this rectangle has got to be a vertical rectangle because it's got to be parallel. So this would be dx. Right? And if you look at the picture there, h would be the height of this rectangle, would be this distance. That's h. And h would simply be the two curves subtracted. It's just because it's just the distance between those two curves. And so h would be x squared minus x cubed. R would be the distance the rectangle is from the y-axis. That's the axis of rotation. So that's r. Since it's just measured from the measured from the y-axis, r is just exactly equal to x. Remember, anytime it's measured just directly from the y-axis, it's just x. So our volume, this isn't too bad, is going to be the integral from 0 to 1, and this would be 2 pi times the radius, which is x, times the height, which is x squared minus x cubed, dx. And so that's actually not too bad. You end up with, take the 2 pi out. This is the integral from 0 to 1 of x cubed minus x to the 4th. That's actually not too bad. And so you end up with volume to be 2 pi times 1/4 x to the 4th minus 1/5 x to the 5th. That goes from 0 to 1. So that gives you 2 pi. Upper limit would just be 1/4 minus 1/5. Lower limit would be 0. So that's 5/20 minus 4/20, which is 1/20 times 2 pi gives you pi over 10. I went through the arithmetic kind of quick there, but pi over 10 would be the volume, pi over 10 cubic units. Disk method. The disk method volume would be the integral from from a to b of pi r squared. And in our picture here, if we're going to use the disk method, rotating around the y-axis, disk method would require a horizontal rectangle. And we'd be rotating around the y-axis. And so notice when we rotate around the y-axis, this rectangle does not even go to the y-axis. And so this would be a disk with a hole in it, right? This is a washer method problem. And so I actually don't have the right form here. This is going to actually be pi times big R squared minus little r squared. And then this would be dy. So it's looking like Shell is the clear winner here on this problem. If we, let's see, let me put this in a different color here. The inside radius would be that distance right there, r. That would be little r, and that would be given by x. And then but x in this case would be equal to the square root of y. And big R, draw it out like that, big R would also be equal to x. It's measured from the y-axis, but in this case, you're out to the cube function, and so that would be the cube root of y. Yuck. And so in our picture here, little r is the square root of y, or y to the 1/2 power, and big R is the cube root of y, or y to the 1/3 power. And so the volume in this problem would be the integral from 0 to 1, pi times big R squared, so this would be y to the 1/3 squared, minus little r squared, y to the 1/2 squared dy. And I want to make sure, before I do anything else, remember that the curves were y equals x squared and y equals x cubed. But those are, I had to solve both of those. Little r and big R are both equal to x here, so I had to solve both of these for x. And so that's how I got the square root of y is equal to x right there, and the cube root of y is equal to x on that one. Because you had to solve both of those for x. And so volume ends up being the integral from 0 to 1 of pi times y to the 2/3 minus y dy. I mean, it's not horrible, certainly, but I think shell in this case is clearly the winner here. So this is pi times 3/5 y to the 5/3 minus 1/2 y squared. And that would be from 0 to 1. Luckily, that's simple. And so that just ends up giving you 3/5 minus 1/2. Those are both tenths. And you end up with, what do you end up with? 6/10 minus 5/10, or 1/10. So you end up with pi over 10 that way also. Okay, so those are examples that compare shell and disk. DeMarco, you asked me about it, and I think this problem is previous problem. It was a wash. They were both about the same. In this one, I think shell is clearly the easier of the two methods. There was just less to do on the shell method. All right.
Oh yeah, I saw that. That was good. Good. That was good right there. Thanks.
Okay, so and I think both of those last two problems are good comparisons, so you can see them side by side also. Okay, so graded homework. So the this was kind of controversial, I guess. Not controversial, but remember, I'm not going to use page numbers anymore. I'm just going to use section numbers, since the page numbers in my textbook, my hard copy of it, are different than your downloaded version. So section 2.1, I think I assigned problem number 2 on that page, right? And then section 2.2, and this was at the end of lecture last time, but section 2.2, I assigned problem number 76. And then section 2.3, this is on the shell method, problem number 122. Usually, so those 3 problems, these are due by midnight on January 28th. And remember that from now on, throughout the semester, homework will be due on Sunday nights at midnight. I want you to turn it into my Dropbox account. So you should be able to go to my Dropbox and plop it in there before midnight. What I'm going to be looking for is that file got dropped in there by midnight. Remember, I need it to be a single file, and it needs to be a PDF. Plenty of apps out there for how you can take your phone and turn it into a scanner. I gave you a list of a couple of them on my Google site and in the syllabus. So be looking for that. And you ought to be able to turn them into a single PDF. So for you guys that are with me today, are you guys okay? Anybody have any questions?
No, sir. I'm fine. Thank you.
Jaime, are you okay?
Yeah, I'm fine.
Okay, so remember I have office hours. Let's see, today is Wednesday, so I have office hours tomorrow from 11 to 12, and then again I'll be online on Sunday evening from 8:30 to 9:30. And if you can't make it during the hours I've been advertising, we can try to come up with a mutually agreeable time. So thank you guys. DeMarco, I'm glad you showed up. Hopefully you'll return for live lecture. And the more people we can get for live lecture, I think overall the better. So you guys both have a great night. Have a great weekend. Please email me, either one of you, if you have questions. And for all of you watching the recorded version, email me and ask me questions. That's great. Okay.